All right, welcome back. So today we're starting a lecture series on the Fourier transform, in particular the discrete or fast Fourier transform. Okay, so let's get started. Fourier transform. Okay, I don't assume that you have any background in Fourier analysis or even really in linear algebra or differential equations. This certainly would help to study Fourier analysis, but really all that we need is calculus. Okay, so we're only going to introduce this assuming that you know calculus, and we're going to kind of derive the important and interesting features of the Fourier transform. Okay, good. And in particular, we're really going to be talking about the discrete Fourier transform. Okay, so the kind of regular Fourier transform you're used to hearing about is defined on kind of continuous functions. But here we're going to be talking about data. Okay. Okay, good. So we're pretty familiar with Taylor series at this point, I hope. We're going to use Taylor series a lot in the section on numerical differentiation and integration, and also of integration of particles through vector fields. So I think it's good for us to kind of refresh ourselves, okay? So I just want to start by saying some functions are really well approximated by Taylor series. Okay. If you don't remember what the Taylor series is, please remind yourself, do some examples. It's very, very important. So maybe I'll just do kind of one quick example just on the side, right? So if I have some function f, let's say that I know my function f about some nominal value, and I also know all of its derivatives. So I know f at x naught, and let's just call this f at some point x, and all of its derivatives. So its derivatives being df dx evaluated at x, d squared f dx squared evaluated at x, and so on. Okay. Then what we can do is we can approximate f evaluated at nearby points to x. So even if we only know this information, right, like my boss emails me f evaluated at x and the derivatives. I don't know what f is. I don't know anything about it except these quantities. Then what the Taylor series allows me to do, or Taylor expansion, it allows me to approximate nearby values in terms of these quantities. So if I have f of x plus delta x, right, so I'm using delta to mean that it's close by, then this is going to equal f of x plus delta x times df dx evaluated at the point x. I know this. Plus delta x squared over 2 factorial times the second derivative of f with respect to x evaluated at x. I'm just going to write the third element because maybe it'll help to understand. Delta x cubed over 3 factorial d squared f, sorry, d cubed f, dx cubed evaluated at x, plus dot, 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 higher order terms. Okay? So this is now written in terms of quantities I know. I know f, df, d squared, d cubed f, all evaluated at the point x. And this gives me an approximation to f at a nearby point, x plus delta x. Okay? So please refresh yourself on this Taylor expansion. It's very, very, very important for almost everything we're doing from here on in. Try it out on some examples, right? See if, so assume x equals 0. That's the base point that we're expanding about. And f of x equals sine x. Right? Try to compute the Taylor expansion for sine x about the point 0. Okay, so that was just an aside. The point I really wanted to make is that some functions, okay, so some functions are well approximated by Taylor series, right? That's what we just wrote here. And I'm going to give you an example. So if my function f of x equals, say, x to the fourth minus x squared, excuse me, this looks like this kind of two-hill thing here. So here's x, here's f. Let's say that this point is 0. So it's kind of symmetric about 0. Then what the Taylor series does, and in the section on numerical differentiation, you can find, I think there will be some codes that essentially illustrate what the different Taylor expansion approximations look like. So if you really are not feeling comfortable with Taylor expansions, you can kind of look for that, that material. Okay, so if we expand this about x equals 0, then our first order Taylor expansion just looks like a line with slope 0. Right? That's just the term we saw, df dx evaluated at 0. It's just a line with slope 0. This is the kind of p equals 1, the first order polynomial. Going back here to the left board, I call these polynomials because I get a polynomial in delta x. Okay? So, you know, if this was f at delta x and x was 0, this would just be f of 0 plus delta x df dx 0 plus delta x squared over 2 factorial d squared f dx squared at 0, so on and so forth. And you can think of this as a polynomial expansion in powers of delta x. Okay, so our first order polynomial expansion, right, power 1, is just this 0 slope line. Our second order polynomial expansion is going to be this parabola looking thing, right? This is p equals 2. My third order, it's a little harder for me to draw, but it's probably something like this. P equals 3. But by the time we get our fourth order Taylor series approximation, we actually exactly represent our function. Because it, in fact, is exactly represented by a polynomial. Okay, so some functions are well approximated by Taylor series, but some are not. Okay. So I would say this as some functions are ill-suited for Taylor expansion. Ill-suited or just bad for Taylor expansion. Okay, so can you think to yourself, what would be an example of a bad function for Taylor expanding, one where it's really going to be hard to approximate it with a polynomial? Think back to your calculus class. What are some functions we've seen that are not well approximated by polynomials? Well, one really good example is a sine wave. Okay, so a sine wave needs an infinite polynomial expansion to be represented accurately. So let's try f of x equals sine x. Okay, here I'm going to have something similar. Maybe this is 0. Okay, that's a sine wave. X, F, sine of X. Okay, so my first order polynomial is going to be a straight line with slope 1. And you can kind of do this on paper and pencil on your own and verify kind of what is the first order Taylor expansion, the second order, third order. Like write down the Taylor series for sine of X and just look at the first term, then both the first and second term, first, second, and third terms, and so on. So this is the linear approximation for a first order Taylor series. A second order one, I'm not going to try to draw it, but the third order just looks like a cubic function, right? And cubic functions have 2 switching points. This is p equals 3. A fifth order polynomial is going to have 4 switching points, p equals 5. But every time I want to capture one more period of my sine wave, I need to bump my polynomial order up another factor of 2. So if I wanted to add another period, then I would have to, or another half period on each side, then I would have to have a 7th order polynomial. Okay, so this is just gets worse and worse and worse. The farther away from my origin I look, the higher order polynomial I need to represent it accurately. Okay, so this is a problem with Taylor series, that they're not good for all functions. Okay? Okay. So the key point now is instead of expanding a function in terms of polynomials, okay, in terms of polynomials, which is what we do in the case of Taylor expansion, it's instead possible to represent our function as a sum of sine waves. Okay, so we're representing our function as a sum of sine waves. Okay, this is the basic idea of a Fourier series. Okay, this is Fourier series as opposed to a Taylor series. Good. Okay. And for example, in the case we were just looking at over here, where we have this sine wave, we need exactly one sine wave of one frequency to represent this. So this is in some sense perfect for a Fourier series. So we only need a single sine wave. For example, 2. And in some sense, this is an example that we cooked up to be particularly easy to represent with Fourier series. But it is still true that there's a whole category of functions that are good for Taylor series and an entirely different category of functions which are good for Fourier series. Okay, good. Great. So now we're going to talk about this theory of expanding functions in terms of sine times some frequency. And in fact, we're going to be talking about doing this purely on data. Okay, so this is not a course on Fourier analysis. And so I'm not going to go through weeks and weeks about converging integrals and orthonormal polynomial or function space bases. It's extremely interesting stuff. Really, some very fascinating and beautiful mathematics goes into understanding the Fourier transforms. For example, we're used to thinking of kind of vector spaces as being directions x, y, and z, for example. But the theory that goes into Fourier analysis tells you that you can also have kind of function spaces that are spanned by polynomials, 1, x, x squared, x cubed, right? And that's the Taylor series basis. And I can also span functions by sines of higher and higher frequencies, sine omega t, sine 2 omega t, sine 3 omega t, and so on and so forth. But that's a little bit, we're getting a little ahead of ourselves, okay? Okay, so this is an entire, there is an entire theory of expanding functions in terms of sines. And I'm going to say sine of k omega x, and this is called Fourier analysis. Okay, that's all I'm going to say about Fourier analysis. Now, we are interested in handling data. Okay, so Matlab, one of the reasons Matlab is so great is because it takes this worldview that data is all that matters. I don't care if my function is smooth or if I even can write down what the function is. Let's say I have an experiment and it gives me data. And I have data at particular points in time or space. How do I do the Fourier transform on data? Okay, so we are interested in data. And the great thing about data is that it actually requires significantly less kind of hardcore mathematical theory. Okay, so there's some beautiful theory underlying this, but doing Fourier transforms on data is not so complicated. So we're interested in extracting frequencies from data. Okay. Now I'm going to give you an example of what this data looks like, and then I'm going to tell you what the Fourier transform is. Okay, so I'm just going to draw a picture of my data. Okay, here we have some function defined on some variable x, and I'm just going to draw some function, okay? But I can't write down this function. I can't say it's 3e to the sine omega t. It's just data at this point, right? I have a bunch of data defined at points x0, x1, ... all the way up to x big N minus 1. Okay, so if you count this, this is a total of big N data points. I'm going to call this F0, F1, all the way up to Fn minus 1, where Fn minus 1 is equal to F of Xn minus 1. We kind of assume that there is a function underlying this, a smooth, well-behaved function, but all I know are these data points. Okay? And we might assume that these are separated by a delta x, some kind of fixed increment where I'm sampling. That's a pretty good assumption. Okay. So the whole goal here is to take a set of numbers, right, my f0, f1, f2, ... is to take my set of numbers f0, f1, dot, 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 fn minus 1. Right? It's just a bunch of numbers that I've collected from an experiment. And I want to go through some procedure, and I want to pull out some kind of frequency components. I want to know, is this thing really high frequency? Is there some low frequency pattern? I want to know what are the frequency components. I'm going to call those f0 hat, f1 hat, all the way up to fn minus 1 hat. And the thing that takes me from my data to my frequencies is called the discrete Fourier transform, the dft. So this is dft. Okay, this is the picture that we're working with today. We have data, and we want to pull out the frequency content. I haven't told you exactly what these mean yet, but we want to pull out the frequency content, and we're going to do it by using the discrete Fourier transform. Good. Okay, so let's just think about that for a minute. And again, before I kind of tell you exactly what those frequencies mean, I'm going to write up the formula that we use to obtain them. Okay? All right, so on a new board, we're going to say what we really want is, okay, we have our data f0, f1, dot, 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 fn minus 1. I'm just rewriting what we had on the other board so we have it fresh in our mind. And we're going to get f0 hat, f1 hat, dot, 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 fn minus 1 hat. Okay, so this is my data. And these are my Fourier coefficients. Okay. So the discrete Fourier transform takes me from data to Fourier coefficients. Dft. And it's just a formula. This is the discrete version of the continuous Fourier transform, for those of you who are familiar with this. We have fk hat is equal to the sum from little n equals 0 to big N minus 1 of my nth data point, f sub n, times e to the minus 2 pi I k little n divided by big N. Okay, now this takes a little bit of parsing, so I'm going to tell you kind of what all of this means. But this is the discrete Fourier transform. Okay, the DFT. So I have data, and it gives me some kind of frequency coefficients. Okay, I'll tell you what these mean. But this is the formula to get them. So it only depends on data and this quantity which I can compute, right? K, I know K. Little n varies from 0 to big N minus 1. And big N is the number of samples I've collected. So let's get our heads around what this e to the 2 pi I stuff really means, okay? So there's a formula called, I think it's called Euler's formula. Maybe I'll do this in a different color. So recall that e to the I theta, right? I is a complex number, the square root of -1. E to the square root of -1 times theta is equal to cosine of theta plus I times sine of theta. This is a very, very useful formula called Euler's formula. Okay, and the way I think about these complex numbers is the following. So e to the I theta is a coordinate in the complex plane on the complex unit circle. So you can verify to yourself that if I take the magnitude of the real part squared plus the magnitude of the imaginary part squared, that's cos squared plus sine squared, That always equals 1. So all of these points have unit length 1 in the complex plane, and the angle is given by theta. Right? This is theta. So my real part is cos theta, and my imaginary part is sine theta. Okay? So that's exactly what this formula is saying. These define a complex number with coordinates cos theta in the real direction, sine theta in the imaginary direction. And so if I look at this quantity 2 pi I times this number, 2 pi is a full revolution of the circle. Okay? So 2 pi I times, let's say, kn over big N. This number kn over big N tells me what fraction of the circle I've gone around. Okay, that's what this geometrically means. These are complex numbers, and e to a complex number is a position on the unit circle. Okay? But you see that these now are frequencies, right? E to the 2 pi I times this is really cosine of 2 pi times that frequency plus I sine of that frequency. So what I like to say is that 2 pi kn over big N is a frequency. Okay, it's some frequency that my signal is oscillating at. And these are the coefficients for that frequency. So I'm taking my original data. And I'm breaking it up into a sum of sine waves of different frequencies. And these f hats are the magnitudes of each of those sine waves. So it's f naught hat times sine of my first frequency plus f1 hat times sine of my second frequency, and so on and so forth. Okay? Good. So I think I'll just give you kind of a sketch of how I see this, even though it's maybe not the most 100% accurate thing. So take this with a grain of salt. Sorry, first I should just write up what is the inverse Fourier transform. So this is what I use. F hats are constructed. Okay, so we go from data to frequency content, and then we can use the f hats to construct f by the inverse DFT. So I DFT. This is not a product that Apple has come out with. This is not the Apple trademarked DFT. This is just the inverse DFT. And that tells me that once I have these frequency components, if that's what my boss sends me in an email is a bunch of frequencies, and I need to reconstruct the data, I say, okay, well, Fn, little n, is 1 over big N, 1 over my number of samples, times the sum from k equals 0 to n minus 1 of fk hat, e to the positive 2 pi I, kn over big N. Okay, so this is the discrete Fourier transform, and this is the inverse discrete Fourier transform. Okay, so it's not so bad. I mean, there's a lot of theory that goes underneath why these are important quantities to look at, but it's really nothing terribly profound at this point. It's just a nice formula that's pretty easy to compute. So the picture I like to think of, and this again is not the complete story, but this is a nice cartoon for your to think about, is that I have some function f on a domain x. This is going to be the exact same function we drew on the right side of the board, basically. Right, we have some function, and let's see, how many data points do I want to have here? I kind of want 4 here, so 1, 2, 3, 4. Okay, I'm going to say that this occupies a length of L in physical space. This is kind of from 0 to big L. This is my length. I'm just trying to give this some physical units because really this is a fantastic engineering tool, and I don't want it to look like it's all math, okay? So what we're saying is that I can write this function as the sum of a bunch of higher frequency sine waves, okay? So f is equal to some zero frequency sine wave, like whatever the distance, whatever the kind of mean of this quantity is just some zero frequency sine wave. So this is mean k equals 0. So here, this is the k equals 0 coefficient. Okay, so that's f naught hat times this plus f1 hat times some big sine wave, right? Some sine of period pi L. So this is k equals 1, sine pi L x, rather pi x over L. So I add the second coefficient times this thing. This is the second coefficient when k is 1, plus f2 hat times the next higher frequency sine wave, which looks like this, right? This is k equals 2, and so on and so forth. And I can add up higher and higher and higher frequency sines, and then I exactly reconstruct this data. And so what this is telling me is how my data is broken up into how big is the mean versus all of these different frequency contributions, okay? And one of the main applications of this is in audio, right? So let's say I have a microphone and I'm sampling some audio signal. I might want to know if it's in C sharp or D flat, and I would know what the note is by what is the magnitude of each frequency component. A really cool example, I think someone should build an iPhone app for this, but to my knowledge no one has. I don't see why you couldn't diagnose the engine problems in a car by taking your cell phone, plopping it on the hood of your running car, and have it listen to the sound that your car is making. And based on the different frequency weights, the kind of energy in each of these frequency bands, you could tell if your Ford truck from 2002 is running how it's supposed to, or if there's some problem. Just kind of a cool idea to throw out there. Okay, good. So we told you what the discrete Fourier transform is. I told you how we get it from the data, and I've drawn the kind of crude cartoon of what it means to me. Whatever that means, it means something to me. Excuse me. So now the final step is how do I actually compute this thing in practice? Okay, I think I don't need any of this anymore. So how do I actually compute this in practice? Because doing a bunch of summations seems kind of tedious. So I'll write down the answer, and then we can kind of convince ourselves that this is true. Okay, so first of all, I'm going to let omega n equals e to the minus 2 pi I over n. Okay, remember, e to the 2 pi I is a full revolution on the complex circle. I'm just going to draw this out one more time. So e to the 2 pi I means I've gone all the way around the circle and I'm here. And if I divide it by n, then what this means is that I've moved only 1/n of the way around the circle. So if n is 10, then this is 1/10 of a full revolution. If n is 9 million, then this is 1/9,000,000th of a full revolution. Okay, that's what this number means kind of geometrically. Okay, what we want is all of our frequency contents, f naught hat, f1 hat, f2 hat, dot, 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 all the way down to f big N minus 1 hat. We want this. I'm going to say this is the Fourier coefficients. Fourier coefficients. And this is our output. This is what we want from our numerical method. And this is going to equal some big matrix, hopefully, times my data, f0, f1, f2, dot, 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 to f n minus 1. Okay, so this is my data in. Okay, so if I can find some big matrix that takes me from my data points to my frequency weights, that would be great, because matrix multiplication by a vector is pretty cheap. Okay, pretty easy to do. So that's exactly what we're going to do. If we just go back to this expression on the left board, we know that each of these fk's is a sum over all of the data times a particular frequency. So this would be kind of a row in the matrix equation on the right. And so that's one thing. And notice that if I have omega n squared, that equals e to the minus 2 pi I times 2 over n. And omega n to the third power is times 3 over n, and so on and so forth. So I can add up, if I want the kth row, if I want the kth Fourier coefficient, then I'm going to add up my data times various higher powers of this fundamental frequency. And it looks like this. So you can kind of check. This is not too difficult to check that what I'm going to write down is exactly equal to the DFT summation. So I get 1, 1, 1, dot, 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 1. 1 omega n squared, dot, 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 omega n to the n minus 1. 1 omega n squared, omega n to the fourth, dot, 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 omega n to the 2 n minus 1. Dot, 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 dot. This is a really big matrix. And then we get 1 omega n to the n minus 1, omega n to the 2 times n minus 1, omega n to the power n minus 1 squared. Okay? Now, this is actually a really easy matrix to compute because I know omega n. So it's easy to compute omega n to the fourth or to the ninth or whatever I want. I can compute that. Okay? This is a big matrix F, capital F, and this is what's called the discrete Fourier transform matrix. I literally multiply my data by a matrix, and it tells me how much of that signal is given by each frequency sine wave. Omega, 2 omega, 3 omega, and so on. Okay? Incidentally, this is called a Vandermonde matrix. You may have heard of Vandermonde matrices in the section on curve fitting. You may not. Okay? But this is the discrete Fourier transform. Pretty simple to show that this is equivalent to our summation on the left board here. And there's an equivalent matrix that takes me from my frequencies back to my data. It's called the inverse Fourier transform matrix, and it's not a lot more complicated. Okay, so that's nice. And again, these F coefficients tell me how much of my signal is given by each of these different frequency bands. Okay, good. So how expensive is it to take data and to compute the Fourier coefficients. Right? We've boiled it down so that it's just matrix multiplication by F, our big matrix. So how expensive is it? How does this scale with larger and larger signals? Okay, how expensive? Any ideas? Well, on the right board, we see that to go from data to Fourier coefficients, we multiply an n by n matrix. And how expensive is it to multiply an n by n matrix by a vector? Well, it's order n squared. Okay, so this is an order n squared operation. Okay, I'm going to tell you about an algorithm tomorrow or in the next lecture called the fast Fourier transform. Now, this is probably the most important algorithm of the last 50 or 100 years. The fast Fourier transform brings the operation down to order n times log of n, which is much faster. I'll tell you a lot more about the fast Fourier transform next lecture. But whenever someone says, I'm computing the discrete Fourier transform, what they really mean, almost always, is that they're doing the fast Fourier transform. So they give you the exact same answer, but this one does it much more quickly. Okay, so FFT and DFT have become completely synonymous because this is such an important algorithm. Okay, great. So now what I want to do is go to Matlab for a moment. And I want to think about a very simple kind of toy problem where we can play around with the FFT a little bit. Okay? So here what I'm going to do is I'm going to clear all of my memory. And I'm going to create a simple signal with two frequencies. Right, this is called the sum of sines example because I'm going to add two sine waves. I'm going to make a really small dt, 0.001, t equals 0 to dt to 1. And then I'm going to say that my data vector x is equal to sine of 2 pi times 50 times t plus sine of 2 pi times 120 times t. So I have omega 1 equals 50 hertz, and omega 2 equals 120 hertz. So in my examples on the board, I said that we were talking about some function f over a spatial variable x. Here I'm talking about a variable x over some time t. You can take a Fourier transform of any data, no matter what it means. In this case, I'm talking about an audio signal, for example. X is the amplitude at some time t, or the voltage coming out of a microphone. So the first thing I'm going to do is I'm just going to plot this. I'm just going to plot this signal. Save this as test FFT1. Okay, and this is what my data looks like. It's kind of noisy. It's not so bad. I think it's actually my Matlab rendering. Right, this is what my data looks like. It looks pretty clearly like there's the sum of two sine waves, maybe. Okay, that's my data. Excuse me. And now what I'm going to do is I'm going to compute the frequency breakdown in the signal. So I'm going to say, okay, n is equal to the length of t. That should be n is 1001. Okay, I'm going to take the FFT of my signal x with respect. Sorry, I'm taking the FFT of my signal x and I'm telling the FFT command that there's n samples. remember, FFT is a fast, discrete Fourier transform. Okay, and what it's going to give me out are a bunch of complex numbers. Remember, this is all e to the I, 2 pi, whatever. And so this is going to spit out complex numbers. But what I'm really interested in is the magnitude of the complex numbers for each frequency. This is called the power spectral density. And it tells me how much power is in each frequency in my original data. So I say my power spectral density is equal to y times the conjugate transpose of y divided by n. So I have to scale it by my number of samples. This is my power spectrum, which tells me how much power is in each frequency. And I'm taking y times y transpose because that gives me that gives me exactly the square of the length of y. Okay, so this is the square of the magnitude of that complex number. And then I have to kind of tell what my frequencies mean. I have to create a vector of frequencies. Freq equals 1 divided by dt times n times 0 to my number of samples. This creates the x-axis of freaks in hertz. L equals 1 to floor n over 2. I'm only going to plot the first half of freaks. And then I'm going to plot my frequencies versus my power spectral density. Okay, I'm just labeling it power spectrum. X label is frequency in hertz. And what should I call the Y label? The Y label is just the power. So bigger Y, more power. Okay, so on the left, this is our original data signal. And on the right, we see this is the power spectrum. So this tells me how much power exists in each of these frequencies. And notice right off the bat, we can see pretty nicely a very good peak at 50 hertz and 120 hertz. That's where all of the power in the signal exists, is at 50 hertz and 120 hertz, which is really good because that's actually the signal that I constructed, right? It's the sum of two sine waves, one of 50 hertz and one of 120 hertz. Okay, so we're going to think a lot more about this over the next couple of lectures. We're going to use this for some great examples in image compression and audio compression and filtering. And we're going to keep building up an intuition for what this discrete Fourier transform really is and what it's useful for. But probably the most interesting thing for us to do is just really get comfortable with using it. Okay, let's take an engineering perspective on the discrete Fourier transform and just kind of explore all of the cool things you can do with it. Okay, that's all for now. I'll see you in the next lecture.